Welcome back to our live training session here with our Honda EP3 Civic. This is going to complete our calibrating process looking at the cold start warm-up enrichment tuning as well as our fuel film tuning. These are the last two things that I always tackle in my calibration process. Now, I've let the vehicle sit here overnight, so we're ready to take a look at the actual cold start, how it's going to be looking at the cranking fuel, if we need more or less cranking fuel, the post-start, and the warm-up enrichment. How all of those tables fit together in order to make sure the engine can crank, fire, and run cold, and then have an appropriate air fuel as it's warming up to operating temperature. So we know on a warm engine, we've dialed in idle, part throttle, wide open throttle, everything's calibrated properly. But now on a cold engine, things are going to be different. So we need to make sure we're applying these correction factors properly. We're also going to be talking about some idle settings and also spark timing compensation when the engine is cold. Recall, we're tuning in alpha N with individual throttle bodies. We have a mechanical-based idle control, meaning we don't have an idle control motor, we don't have drive-by-wire to be able to bring more airflow into the engine. So we need to get creative by allowing the engine to make up for the lost torque from the frictional drag of a cold engine. We also have a wall wetting effect going on where the fuel is not going to get into the intake as easily because of the poor atomization from the injectors on a cold engine. So we're going to be using some compensation tables, post-start warm-up enrichment, as well as a lambda offset when the engine is cold to achieve a better torque output and a more stable idle as it's coming up to operating temperature. So let's just jump in here and take a look at a few things. So first things first, I'm going to jump into my fuel tuning page because I have the parameters. If you look under our channels list, coolant temp and intake air temp. Now, if you recall when we were going and doing in a third tutorial, the sensor check, I noted that the coolant temperature wasn't correct, at least the scaling wasn't correct because it wasn't matching close to the intake air temp. Now, on a key on engine off cold engine, these two should be within 1 to 2 Celsius of each other. We can see right now I've actually fixed the coolant calibration scale on my calibration table for the coolant temp sensor, so it's actually going in and registering a reasonable coolant reading. Before it was about 8 or 9 Celsius if the ambient temperature was showing about 18 Celsius. It was off quite a bit. Now it's actually really close. It's important that we have an accurate coolant temp because it's going to be used for the compensations for post-start and for warm-up enrichment and also for taking a look at cranking fuel. So we want to make sure that we're tracking that correctly. So I have fixed that. I wanted to note that before we go in here and do any actual tuning. So the next thing I want to do is just talk about where we're at in terms of our startup fuel window here and how the closed loop or the cold start routine is going to go and how everything's going to fit together here. We're also going to take just quickly a look at idle tuning and then also talk about our ignition timing and what we have in place when we built the base map to allow us to hopefully have a successful cold start here. Because again, we know everything is dialed in warm. Now we're allowing these multipliers, these compensations to take place and add additional fueling to make up for a wall weighing effect that we're trying to compensate for. So first things first, when we're talking about our cranking fuel, we're seeing our cranking fuel table is based on coolant temp, and it's also based on engine crank cycles. Now, on a warm engine, the values were correct. I could crank and fire the engine pretty much right off the bat. On a cold engine here, we'll see how many cranks it's going to take for the engine to fire off. If we're finding it takes a lot of cranks, extended cranks for it to actually fire, that could mean that we need more fuel in here. It could also mean that we're not achieving cycle lock quickly with our cam and crank pattern. So the ref sync, if we actually go in here to our setup window, into our ref sync, we have our engine speed reference state. This should show cycle lock. Once it shows cycle lock, that means that it's registering the cam and crank pattern. Everything is good there. It's synced up. It's then firing the coils and injectors. Until this shows cycle lock, your engine's not going to start. So if you're having problems cold, let's say, and you're trying to crank over your engine and you're not achieving cycle lock right away and it's taking a lot of cranks to fire off, it is not a cranking fuel problem. You don't need to go and increase your cranking fuel. You have to figure out why it's creating a problem for you within your ref sync settings here. So I want to note that, and we'll actually review this when we look at the data log and kind of play it back and take a look at everything. So let's jump back in here let's go back into our tuning. So we'll figure out if the cranking fuel needs to be adjusted, how many cranks it takes to fire off. We have our cranking airflow. This is not relevant on a mechanical-based idle, so we can ignore that. Cranking spark timing, this is something we may need to adjust. If we have higher cranking spark timing here on our colder coolant temperature, this is going to allow us to have a little bit more cranking torque. This may or may not be beneficial. I'm going to keep the values all around 5 degrees spark advance in cranking conditions. We'll have to see how it performs. This could be something we want to adjust. If we have a little bit more cranking torque, we bump our spark timing up. That could allow the engine to fire a little bit easier. But we can also go the wrong way with it, having too much advance and actually getting kickback on the starter, which isn't good for the starter or the engine. So I'll keep it at 5 degrees, and we'll have to kind of evaluate just our fuel to see where that's at. Now, once the engine actually fires off for the first few seconds, we'll be in our post-start table. Coolant temp versus our engine runtime here in this table. We're adding a decent amount of fuel here for the first 10 seconds, and then it zeroes out. We always want to make sure in our post-start table that the last column here is always all zeros. Really important, otherwise your entire fuel and airflow model will have this percentage correction added to it at all times, which obviously skews up things and it's not desirable. So we always want to make sure this is zeroed out. Also, closed loop correction can't kick in until the post-start is dissipated here. So right around 10-second mark, we should find that the post-start comes online, or the closed loop comes online, because the post-start actually turns off. So if that makes sense. So we'll be watching what the closed loop correction is doing, kind of getting a feel for that. We also have our warm-up enrichment, and this is the long-term multiplier that's going to add additional fueling offset versus our coolant temp. So we are only in the post-start for first few 5, 10 seconds, 20 seconds. This allows the engine to stabilize. Then we transition into the warm-up enrichment. This is applied long-term until the engine actually comes up to operating temperature. Now in here, I have it zeroed out between 40 and 100 Celsius. I'm gonna consider this area to be kind of the engine warmed up, and I'm not concerned with having to add any offset, although we'll have to see how that goes as the engine warms up. But as the engine's here in the cold temps and starts to transition into that warm-up range, we may need higher values in here. Now the values that we have in the table are default values from Motec in the base file that we started with, so this likely is gonna need to be changed. Also, the post-start likely is going to need to be changed, but we'll keep an open mind with this, and we're just going to test it as is to figure out where we're at as a baseline and then what adjustments we need to make. Now, the other thing we have going on here is our lambda ECT offset. Lambda ECT offset is based on coolant temperature, and recall that the Motec will always use the lowest command at lambda across all of the lambda tables. We have our lambda aim right here. We know that we have a lot of different compensations can be applied. Anytime you see a value of 2.0, that's essentially saying bypass it, turn it off for a compensation. But anytime you're noticing that there's values populated, so here 0 to 30 Celsius, I have values of 0.9 lambda. That's going to override what I've commanded here at idle in that same area, so 1.0 lambda. We're going to be targeting a richer target lambda mixture for the first few, let's say, minutes as the engine's warming up. And this will allow the engine to idle a little bit more stable. It'll also increase our fueling delivery to our engine, so it has a two-part effect. It also gives, when the closed loop turns on, a corrected target to shoot for and make adjustments against. And we're using the closed loop correction to actually guide us in updating the post.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.